Started. Welcome to the AI session of FDF 26. I'm happy to introduce our second keynote speaker, Thomas Gmeinder. He is an accomplished and skilled engineer with more than 24 years of professional experience with years in artificial intelligence applications in the cloud and at the edge. He has years of experience with embedded hardware and software design, and also years of experience with AC verification with a focus on processors, and years in customer supporting roles. He's very passionate about growing the adoption of AI in a responsible manner and technical sales and nature. And today he will be telling us about AMD's embedded AI solutions. Welcome, Thomas. Feel free to start.
Thank you very much. Hello, everyone. I hope you can hear me okay in this great auditorium and you enjoyed I get the thumbs up from the back. Great, thanks. And I hope you enjoyed your coffee and cake. And I'm happy to talk about the solutions that AMD has in the embedded AI space. So I work for AMD in Munich and work with lots of customers across the landscape of AI embedded systems and help them integrate AI into embedded systems. So let's get started. So I want to give an overview of the requirements for AI processing in the embedded system and the AMD platforms that exist for this. Then talk about two clans, really. So one is the embedded x86 portfolio, which we call APUs. APU stands for Accelerated Processing Unit because they integrate a CPU, a GPU, and an NPU. So three subsystems you can use for AI acceleration. And my colleague Thilo yesterday gave you an overview of the whole spectrum, and I want to concentrate on a few families. Then also about the adaptive SoCs, which I'm sure many of you are familiar with. So the FPGAs and more recently the Versal adaptive SoCs, including AI engines. Then we talk about the software stacks, and a system is only as good as the combination of the software and the hardware. So the AI stacks are very important to make efficient use of the hardware for the acceleration of AI models and systems. And finally, we talk about a few applications to give you an idea what's hot. So starting with an overview of the requirements for AI processing in the cloud, on the edge, and on the endpoint. So you see from the lack of overlap in this spider diagram that the requirements are really diverse. So in the cloud, you want to maximize compute and memory bandwidth, and you have all the power that your power station can produce. On the embedded system, if you have a battery, it's completely the opposite, right? You need to save power. You need to make do with the compute and memory resources you have available on your power-constrained system. So a wide range of requirements. So you require different targeted systems, of course. And I want to give you an overview first of the whole spectrum of the hardware and software that AMD has for the endpoint, in the middle, the edge, and for the cloud. And then focus and drill down on the two clans in the embedded solution space. So let's do that. Oh, by the way, at the bottom here you see the various software stacks that are used for AI acceleration on these hardware systems. So going down one level, you see now on the left, I called it the APU clan, different families. So the Ryzen Embedded 8000 all the way to the leading flagship X100. And I go into more detail about that. And the other clan is the adaptive SoCs. I'm sure you're familiar with AMD Sync, Versal, and most recently Versal AI Edge Generation 2. So let's look at the hardware subsystems that are used for AI acceleration on these hardware platforms. So for the APU, again, accelerated processing unit, we have a CPU which has vector processing or vector acceleration instructions. So the Zen 5 architecture has AVX 512 instructions, allowing you to multiply vectors of 512 bits in one cycle. So this gives you around 10 TOPS in the high-end device, which I will show you, which has 16 CPU cores. You get like 10 TOPS, tera operations per second is the unit for AI compute for the CPU. Then a very powerful integrated GPU you can use for AI acceleration, giving you up to 119 TOPS, and giving you on the high-end device up to 256 gigabytes per second. I get into why this is important later when I talk about LLMs. And then we have the NPU, which is what is shared between the APU and Adaptive SoC families, and a major reason why AMD acquired Xilinx. So this, you're probably more familiar with the name AI engine. So a systolic array of AI engines is what is called an NPU, neural processing unit. And that is the same piece of hardware that is used in the x86 embedded APUs and the adaptive SoCs, as we will see in more detail. And we also go into more detail about the kind of models that are supported on these various subsystems. So we are now at a state, so it's progressing really fast. We are now at a state where you can run large language models up to a size of 20 parameters, 20 billion parameters, pretty fast on a embedded system, giving you a lot of the advantages of local processing, data privacy. You don't have to send it off to the cloud, and you don't have to wait for it to come back, so you're saving the network latency. And you can run models up to 70 billion parameters, and they are powerful models, intelligent models on the high-end APU locally, but I get into that later. On the NPU, we can also run LLMs, but the NPU is more specialized for convolutional neural networks. And this is why. So let's talk about what the NPU is. It's a systolic array of high-performance processors that can do very fast matrix multiplication and overlap with the VLIW architecture, overlap the compute with the loading of the next data. So making this a very efficient engine with very high compute density. And as you see, also very high memory bandwidth, because each AI engine has 64 kilobyte local memory and can access the local memory of all its neighbors. So this gives you a very large aggregated local memory bandwidth, thanks to the 512 bits memory interface. And you can connect to a higher level memory with the memory tiles, and they have 512 kilobytes each. And this architecture is scalable because it's modular, so you can build arrays of different sizes. The largest one is containing 144 AI engines. And then, of course, you can connect to higher level memory like the DDR. But there's a lot of very fast local memory and a lot of compute performance for the good old matrix multiplication, which is the foundation of many DSP algorithms and also many AI algorithms. So let's talk about more details on the APU portfolio, giving you an overview of the capabilities in terms of compute, memory, and what kind of AI models they are targeted for. So you see, on the left, we have the Ryzen 8000 family with up to 8 cores with the Zen 4 architecture. RDNA is the GPU architecture, Radeon DNA, and then XDNA is the AMD marketing term for the AI engines. So XDNA is AI engine ML, and XDNA2, which you get from from the P100 up to the X100. This is what you might have heard of under the name AI ML version 2, so the second generation of the ML version of the AI engines. We also have a wide range of memory bandwidth here, from 90 gigabytes per second up to 250 gigabytes per second. And in terms of the GPU performance, from 16 TOPS to 59 TOPS. And finally, the NPU, the third important subsystem for AI acceleration, giving you in the 8000 family 16 TOPS up to 50 TOPS in the other three variants. And then what workloads can you accelerate locally with these family members? So for the 8000, it's LLMs below 8 billion parameters and CNNs, and then going all the way up to LLMs with 70 billion parameters, and text-to-speech, speech-to-text models, vision transformers, vision language models. They are large language models trained with images, images and text pairs. So by training them in this way, you essentially teach them to understand images, and then they can describe images, becoming multimodal in this way. They are called vision language models, and then vision language action models. They are similar to vision language models, but specialized for robotics, in that they output not just a text description of the image, but they can also output direct commands for the robot, direct actions for the robot. So like JSON output telling the robot where to move the arm to open a door. And we have reached the age of agents. So chatbots are yesterday's technology. Well, agents built on top of chatbots, right? But they are also now very relevant for the local AI processing. You can run your coding agent or your co-working agent locally on your PC, doing stuff autonomously. And that's really what sets them apart from chatbots, where you have always a user prompt and a response, like the ChatGPT style interaction with an AI system. And agents are more autonomous. They can execute tasks autonomously, and they get from the model the response, like call a tool, do a web search, call a tool to open the car window, call another tool to set the navigation system, and so on. So this is what agents do, and they put more requirements on the CPU processing. So all this orchestration and the context management of the large language model, as well as calling the tools that they get back from the response of the LLM, this is all needing a lot of CPU processing. So this is the high-end device, and it's based on AMD chiplet technology. There are 2 chiplets on the top with up to 8 CPU cores, giving you a total of 16. And they are connected on the substrate with a system die. And the system die integrates the GPU with up to 20 working group processors, the NPU with up to 50 and 8 TOPS, and as you see, all around the edge of the left and right-hand side of the system die, the peripheral interfaces, as well as up to 8 memory controllers. And they are LPDDR5X, giving you a total aggregate bandwidth of 256 gigabytes per second. And that's really key, that the external memory bandwidth is key for the performance of your LLMs, because from a certain size, about 2 billion So the thing that stresses the thing that makes the LLMs memory bound is the fact that for generating a single token, you have to load all the parameters of the model for each token. So that directly determines the tokens per second performance you can achieve with your given memory bandwidth. Because for a 4B model quantized to 4 bits, you have to load for every token 2 gigabytes. And that's why it becomes a memory-bound workload. And with more memory bandwidth, you get more tokens per second. Yep. So giving you a bit of an overview regarding the stack, the AI stack capabilities. So what we have now is good ROCm support for the iGPU. AMD has invested tremendous resources into making the ROCm stack perform well in the cloud. And all this development is coming to the embedded system. So ROCm support is important for general PyTorch models. Then the NPU is supported on Linux since the last version. And what's coming up is custom operators. So I think there was a question yesterday about how can we use AI agents, coding agents, to maybe bridge the gap between the high-level model and the low-level execution on the AI engines. And when I talk to our R&D guys, they tell me that it's actually a very good use case for Claude Code to tell it, hey, I have this custom operator in my Onyx model that is not supported by the compiler yet. Write me a custom operator. And it does a pretty good job at that. First writing it on one AI engine and then making it parallel. So the compilers are getting competition from the coding agents because the coding agents can generate the low-level code in a fast way in a similar quality to the compiler. So that's an interesting use case for coding agents. Parallel execution is also an important feature because I showed you earlier we have 59 TOPS on the GPU and 50 TOPS on the NPU. So a lot of AI compute that you can use in parallel because they are distinct parallel subsystems. And this is also that will be supported in the next release. Custom operators and parallel execution. And finally, a hybrid mode. For some models, it makes a lot of sense to use the NPU for one part and the GPU for another part. LLMs, you always have the prefill stage, where, especially with agents, you have a growing amount of context. So you want to give the model some context about the question you are asking it or the request you give it. The context in a RAG system is documentation, or in an agent system, it's what was the conversation up to this point. And it needs to know that context to give a proper answer, but you have to pre-fill that context, and that is a compute-bound workload, meaning the NPU is good for that. So the prefill is running on the NPU, and then the decode is running. So the decode phase is where it starts generating text in an autoregressive manner. I told you earlier, for each token that's generated, you have to load all the parameters from the memory, and this is where the iGPU shines because it has a very high external memory bandwidth. So this is a prime example for using both the NPU and the iGPU in concert for a acceleration of a single model like an LLM. So let's move on to the Adaptive SoC portfolio. This is an overview of the Versal Gen 2 architecture. It has really enjoyed upgrades across the board compared to the Gen 1 architecture. The biggest improvements you get in the processor subsystem, where you get up to 10x the scalar compute performance. up to 200 DMIPS from 8 A78 cores and 10 R52 cores. There's also improvement for safety. The lockstep feature was added to the application processors that doesn't exist in the Gen 1. So now you can run the application processors and the real-time processors in lockstep, which allows you to achieve ASIL D certification. Then upgrades on all the serial interfaces like PCIe, upgrades on the memory performance. I told you earlier how this is very important for memory-bound workloads to get higher memory bandwidth. And then the next generation AI engines, adding advanced data types like MX6 and MX9, giving you more TOPS for your AI acceleration. The addition of ISPs is also important for vision applications where you want to do your image signal processing in an optimized, hardened component. And there's also a GPU that was added, but this is more for graphics than for AI acceleration. And the flexibility of this architecture enables you to connect any number of standard and proprietary sensors that you often have in embedded systems. I'm sure you have a large choice of proprietary sensors here at CERN. And one of the features that makes this possible is the programmable logic that I'm sure many of you know. So it makes it very flexible to implement proprietary, fast and scalable interfaces in this programmable logic. And in addition, you have the DSP engines, which are key for accelerating many DSP algorithms and also AI models, because the foundation of many DSP algorithms and AI algorithms, as I said earlier, is the good old matrix multiplication, which this does really fast. And I want to remind you of the AI engines as well that sit in parallel to that, giving you even more compute density for these mathmal-heavy algorithms that you might have. And I want to look in the context of the architecture of the three phases of processing in AI-driven embedded systems. You usually have one or more input sensors that you have to input from, running some hardware interface, then some pre-processing you might want to do. You can use the ISP, hardened ISPs for images, or other PL or PL resources for like normalization. And then, of course, important for AI is the inference speed. So you have a certain timing budget, and in this time you have to run inference of your model on one or more samples that you receive from your sensors, and then you get outputs. So we're showing a demo for YOLO, where you get where your output is a set of bounding boxes for each of the detected objects. Then you have to run an NMS algorithm to find the optimal bounding box, and then you have to display what is detected. Is it a person? Is it a laptop, etc.? And this is all part of the post-processing. Giving you an example for agents where you get the output from an LLM. The agent then has to read what tools it has to call and then do a web search if the LLM says, I want to do a web search, or call some other tool like opening the car window or setting the navigation. So that's done in the post-processing. And now let's look at which hardware subsystems are useful for this. You might have guessed programmable logic for the pre-processing and the sensor inputs, then AI inference, the AI engines with the very high matrix multiplication, compute density. And for post-processing, the CPUs, again, now with agentic AI, there is more demand on CPUs, and you have a high number of CPU cores available in both the adaptive SoCs and the x86 APUs. Here's the overview of the adaptive SoCs, again, ranging from, for the CPU compute, ranging from a small number, 15K DMIPS, up to, in the latest generation, 200K DMIPS. And the tops are also scalable from around 8 tops for int 8 up to the 202 tops for int 8, and various package footprints. There's, of course, all this information and more available on the web. Now I want to show you an overview of the compute and memory comparison across all of the embedded portfolio. So on the left, you see the consideration for the int 8 tops, and you see there's a mix of adaptive SoCs like Versal Edge and Versal Edge Gen 2, so 2VE is for the generation 2, and mixed with APUs from the x86 portfolio. So the highest score for the memory bandwidth you get for the X100, and the highest score for the tops you get from the Versal Gen 1. But the Versal Gen 2 is pretty up there with almost 200 tops. But again, the X100 gives you the maximum bandwidth, which gives you the best performance for local LLM inference. On the right, we're looking at different data types, like FP16, BF16, which is brain float 16, which has the same dynamic range as FP32, but in a 16-bit data format. And then BFP, block floating point data types, which are becoming increasingly important because it's all about saving memory with these large LLMs, with these memory-bound workloads, and block floating point formats. They allow you to save memory because they share the exponent across several mantissas. So in MX6, you have an 8-bit exponent shared across a range of mantissas, and then compressed, which gives you a high memory efficiency and up to 369 tops on the Versal Gen 2. Last but not least, I said at the beginning, the whole system depends on how efficient the software runs on the hardware, right? So let's talk about that before we talk about some applications. To give you an overview of what kinds of models are supported, so the models are categorized into CNNs, vision transformers, audio models, large language models, and vision language action models. And the broadest support you really get from the iGPU. That acceleration is based on ROCm, which has enjoyed a lot of improvements. But the NPU is catching up quickly. On the Ryzen AI Embedded processors, we have support for CNNs, vision transformers, audio models, and also LLMs. And VLA will also come. This needs to be updated. Then the Versal AI Edge Gen 2 is in a category of its own because it has its own compiler, which is the same compiler that we use in the APUs. I told you earlier that the NPU is based on the same hardware architecture, the same AI engine MLv2. So they share the same compiler, and that's why you have similar model support for Gen 2. And then we also have the other families, the Versal AI Edge, the AI Core, and the Sync MP SoC families, where CNNs are supported. And to give you an overview of the whole stack, it's very busy because there's a lot of, well, you have the two major frameworks, right? You have TensorFlow and PyTorch. We have to make sure that these models execute efficiently. You have the common format, ONNX, which is used to exchange models between TensorFlow and PyTorch, making use of the PyTorch compilation and graph optimization. And we have to make sure these models efficiently run on all of the subsystems that we can use for AI acceleration. So we do that by using different backends. We have ROCm or Vulkan. They are both open source, but ROCm is the AMD focus or the AMD product. It's open source, and Vulkan is an open source community project also for the acceleration of AI on the iGPU. And then we have AMD Versal AI software stack for the NPU, and we have CenDNN for the CPU. I was shown the 5-minute sign, so I better hurry up. So this was for the APUs, and this is the software stack for the adaptive SoCs. Again, we are supporting ONNX, TensorFlow, and PyTorch to make sure that these models run efficiently on the hardware accelerators, which are the NPU on Versal AI Edge Gen 2, and on the MP SoC. We don't have AI engines. We do this AI acceleration on the PL with the DSP slices. And last but not least, let's talk about some applications that are possible using this hardware and software for embedded AI. This is the demo we're showing in the coffee area. It's running 4 YOLO V8M models completely in parallel. It can do that because it uses 16 AI engines for each model, and we use a chip where we have 64 AI engines. So they run completely in parallel on this systolic array, and each YOLO V8M model runs at 30 FPS, giving you an aggregated performance or throughput of 120 FPS. So please come and have a look and have a chat after this. Another cool or AI-enabled application is optical flow, important in automotive use cases or robotic use cases. In this case, it's a raft large model, which gives you a prediction for every pixel, where it moves and how fast it moves. And you see this in this vector field down here, how fast they move. So the biker moves to the right, and the background moves to the left. And this, yeah, you have to look more closely to see the direction of the arrows. But here on this color encoding, you see that the biker has a very different movement from the background because it's a very different color. And this runs with 30 FPS on a X100 high-end GPU, an integrated GPU. And I talked a lot about LLMs and local AI agents, and they are here. So if you are used to working with Claude Code, you know what an agent does, and this you can do now locally. So a big step forward for the usefulness of chatbots and LLMs was the fact that they learned to call tools. So if they need more information to answer your question, they can call tools like a web search or call your RAG system to retrieve documentation. And this ability you now get locally. So this is running on the NPU. It's a Gemma 4 is a tool from Google, a model from Google, the open source version, the latest model, which can do web search. So you have that experience from ChatGPT or Claude Code locally on your machine now. And these are the web resources you can use for that. So on the left, you see the AMD AI playbooks. If you log on to developer.amd.com, you get free credits to high-end GPUs if you want to do some model training or fine-tuning. And you get some examples for running AI models locally on your Ryzen AI processor, which you might have in your laptop. And on the right, the examples for the Ryzen AI Onyx models. So in summary, AMD offers a broad portfolio of x86 APUs and adaptive SoCs for AI acceleration. I hope I could explain well why we need a heterogeneous architecture, why we need for some processing the PL and for other processing the AI engines and the CPU for the post-processing work and the orchestration of AI agents. And this is that unique combination of CPU, GPU, and NPU and programmable logic that is combined with open source software stacks, which enables the local intelligence now, and because it's predictable, scalable, and functional safety is also an important consideration. So we think we have a powerful offering that is fit for the future. Thank you very much.
Thanks, Thomas. Thanks a lot, Thomas. Questions or comments for Thomas? Here, go ahead.
Hi. I'm interested in the Versal mostly, as I guess a lot of people in the audience are. So I'd like to know a little bit more about the interconnects. Like you showed the various components of the device, including these AI engines, of which I think here at CERN we're mostly interested from in ML rather than LLMs, right? So what's the kind of interconnect there if I want to use the programmable logic and those engines? Like where we often get the benefit of FPGAs is in pipelining, right? So sometimes we don't care about the latency so much because we just want to keep the thing busy, right? So we pipeline, and that's the advantage of the FPGA over, say, a GPU. But can I use pipelining, and is there like an internet connect to the AI engine so I could do some ML there, get my data from my pipelining in there and back out? Or do I have to go through the CPU on board? Or how does it work exactly?
Thanks for the question. So I talked a lot about the performance of the individual components, but as you say, they only work as well as they can communicate. So in the adaptive SoCs, there is the network on chip architecture, which is essentially a fast bus that connects the processor subsystem, the PS, with the programmable logic and DSP slices and the AI engines. So on the adaptive SoC side, it's the NOC that allows you to do that, to set up this highly programmable and very efficient, very silicon efficient communication between the subsystems. And on the APUs, on the x86 side, we have the Infinity Fabric. I think it was on one of the, on that very busy block diagram of the X100. In the middle of this system die with the memory controllers on each side, you had the Infinity Fabric. And that connects the CPU. And one level below, you have the chiplet architecture, where you have the fan-out connecting the individual chiplets. But the interconnect is called Infinity Fabric. But yeah, thanks for the question. It's very important to have efficient communication.
Okay, so you could load a model onto the AI engine and then pipeline data into it and then back out?
Yes, the pipelining aspect is important as well. And within the AI engines, you have this I talked about the local memory access, and I talked about the access to the memory ties, which goes via the NOC. What I didn't talk about or explicitly mention was this forwarding bus. So it has built into the architecture the ability to build a pipeline with using multiple AI engines within the array, because you can forward partial results onto the next AI engines, building DSP pipelines or indeed AI model pipelines. So that's within the AI engine, and then of course you can pipeline stuff, do your pre-processing in the PL, and pipeline that to the AI engines via the NOC.
So
but
can you go directly from the programmable logic to the AI engines, or you have to go through the PS?
You can do that with DMA.
Okay. All right, thank you.
Which is highly programmable as well. So making sure that as soon as the PL has sensor data, it's consumed by the AI engines.
Thank you very much.
Any other questions from Thomas? Go ahead.
Okay, thank you for the talk. Am I audible?
The red light's on, I hear you.
All right, cool. Just how do you say, continuation of that. The Gen 2 numbers are quite impressive, but what I find difficult is when you want to program, say, between the AI tiles and the PL, I think you need like a C++ programmer, a HDL programmer, and also a bare metal.
If you do purely AI, you don't have to go to that level, because the compiler consumes your model in Onyx or TensorFlow or PyTorch. But you can have a look at that level, but you don't have to understand it to accelerate AI models.
But if I want to, say, implement a DSP model, say, beamforming on it, then I would need this, right?
Then you would need to use a different tool. So this presentation was about Vitis AI, which is the AI stack for the AI engines. If you want to do your own algorithm development on the level of the AI engines, you would use that dialect called ADF, Advanced Data Flow, or Adaptive Data Flow. And for this, you would use the Vitis tool, which gives you an idea of which kernel runs on which AI engine and how do they communicate, giving you that level of abstraction.
So my question was just that, is there a plan to kind of put that together, or this is kind of kept it for that complex cloud, so to say?
No, but in terms of visibility, the AI stack has a tool called AI Analyzer, which allows you to see that level of abstraction of the AI engines. Which part of your model are running on which AI engine? You get that information just from a different tool, which is more tailored for AI. Because for AI, you really want that connection between your Onyx graph, which shows your model in a graph view, and how that graph maps to the AI engine array.
Okay, thank you.
Thank you.
Go ahead.
Thank you so much for your presentation. I have one question. Given that your information that you give us, NPU is optimized for low latency inference, and our integrated GPU is used for the larger and memory-hungry workloads. My question is this: if you would like to partition one vision transformer, for example, for autonomous vehicles on your AMD devices, how do you partition that between two engines? Which part should be remained on NPU? Which part should be remained on integrated GPU? For example, image preprocessing, vision transformer, backend, segmentations, or attention-based anything. Thank you so much if you answered this question.
Thanks for the question. So your question is about how do you control the partitioning of different models. You control that with using the execution provider for the backend, for the Onyx runtime. So for the NPU, it's called Vitis AI Execution Provider, and this is where you compile your CNN. And the vision transformer, you would compile with the MIGraphX execution provider, which is part of ROCm. And that would take your vision transformer in Onyx and do the graph optimization and run it efficiently on the iGPU. So it's on that level of the execution provider that you decide which model goes to which hardware.
If I understood well, you mean that, for example, the pre-processing task, for example, pre-processing the image from the radar or any repetitive task are done on NPU and always on vision transformer. But if, for example, using ONNX for creating vision transformer, it's done on integrated GPU?
This is your decision. So, well,
okay.
not entirely. At the moment, it's only possible on the iGPU.
Oh, now it's only on iGPU. Okay.
Yeah.
The pre-processing of the images for radar and camera is done on NPU or on integrated GPU? Which one? Now, currently in the reality.
So, are you talking about the demo we are showing or a general example?
No, about the demo.
Okay,
Yeah.
the demo. So the demo showing, it shows four camera inputs with over MIPI with 4 HD frames essentially in parallel, and then this is done using the pre-processing is done with the ISPs that are in hardware, and then it's passed on to the AI engine array, where we have 4 instances of YOLO V8M running completely in parallel. And that's why we get the overall performance of, or throughput of 120 FPS, 4 times 30.
Thank you so much.
Okay, great. So in the interest of time, I think we do need to move on to the next speaker. Thanks again, Thomas. If you have more questions, feel free to go to the AMD booth outside to ask more questions.
Yes, I'm happy to chat. Come by. Thank you.
Great. Thank you so much.